So exercise 22.3 is asking you to draw the two possible enols. We've introduced that concept in the last two videos. That can be formed from 3-methyl-2-butanone. And also to show a mechanism for how each of those would be formed under, crucially, base-catalyzed conditions. Well, the first step is just to know what we're dealing with. What is 3-methyl-2-butanone? You'll note that you have hit the last branch because it'll be the last YL. And whatever you have after the last branch, that's your backbone. Draw that first whenever you're going from a name to a structure. The prefix is but, so we know we have 4 carbons. So 1, 2, 3, 4. And I'll number that just so I can keep track of things more easily. Then the infix is AN, so all single bonds between those. The suffix is ONE. That means we're going to have a carbonyl, where the carbonyl carbon is surrounded by 2 carbons. Where does the carbonyl go? On carbon number 2. So we have our ketone here. You'll notice carbon double bonded to oxygen with a carbon on both sides. So that's 2-butanone. But we also have a methyl group on carbon number 3, so 1 carbon coming off of there. And there it is, 3-methyl-2-butanone. Okay, so they want us to show how this molecule can turn into 2 different enols under base-catalyzed conditions. Okay, well, if we're going to do this twice, we are going to need 2 versions of this molecule. And let's actually get a little more space. Oops. Okay. Now, a base, and they don't give us a specific base, they just say under base-catalyzed conditions. We'll see several different bases in this chapter, but one that we'll see fairly often is hydroxide. That's one you've seen plenty times before. So hydroxide is going to try to snatch a hydrogen. But what hydrogens are most vulnerable on this molecule? What hydrogens, if they're stolen away, would leave the electrons in their bonds at a place that can stabilize them? And what you might see is that it's the alpha hydrogens. Now there's one on both of the alpha carbons. Remember that the carbonyl carbon is the carbonyl carbon, and the carbons next to it are the alpha carbons. So we have 2 alpha carbons here. Both of these have at least 1 hydrogen. So those are 2 possibilities. And actually, let me do that. Okay. Okay. So the reason why you can get 2 possible enols is because you have 2 possible alpha hydrogens. What ends up happening is this base steals one of these alpha hydrogens, and the electrons in the bond to that hydrogen snap back onto the carbon that the hydrogen was on. So really what we're doing here is a proton transfer. And remember, anytime you do you show how a ketone is turning into an enol, it's always just 2 proton transfers. So that's our first one. We end up with a structure that has a lone pair on a carbon. Carbon is not usually able to stabilize lone pairs with a full negative charge. It's not a very big atom, so it can't dilute the charge over space. And it's not a very electronegative atom, so it can't pull the electrons toward the nucleus to stabilize them by getting them close to the positive charges of the protons in its nucleus. I'm going to erase the other alpha hydrogen for this so it doesn't distract us. We'll see how that behaves in a second. But the reason why this carbon can handle that negative charge in that lone pair is because it is allylic to the carbonyl next door. This lone pair is 1 atom away from an atom in a double bond. And so what you have here are p orbitals. You have 2 p orbitals here that are giving rise to the pi bond, and then this lone pair is existing in a p orbital, and so the electrons can spread out through all of those places. Anytime you have an allylic lone pair, that happens, and that helps to stabilize the positive charge. that is what's diluting it in space. You'll notice that when you have that allylic lone pair, that's a resonance pattern. And so really what we'll have here are two resonance structures. When you have an allylic lone, so we draw the brackets that warn people, neither of the structures in here are the true structure. The true structure is only, ever, and always the average of the two. That special resonance arrow with the one line and two heads reminds people to take the average of the two, and is very different from an equilibrium arrow. So when you have that allylic lone pair, to get the other resonance structure, you draw that lone pair forming a pi bond toward the pi bond, and the pi bond breaking and forming a lone pair away from the lone pair. So when you do that, you no longer have the lone pair, you're going to have another pi bond there. And the pi bond in the carbonyl won't be there anymore. It will be a third lone pair on that oxygen. And the oxygen has a full negative charge. If you compare this with the mechanisms that we drew in the last couple videos, you'll notice that this is not quite an enol. It's very close. You have the double bond, and you almost have the alcohol, but the oxygen doesn't have the hydrogen yet. It has a negative charge instead. And so this is called an enolate. An enolate. And you have the double bond, you have almost the alcohol, but it lost its hydrogen, and it has the negative charge instead, that ending ATE. If you add it to the end of a name that would, for a normal molecule, means that it has a charge. So we saw carboxylates, for example, when after the oxygen, the hydrogen in the carboxylic acid gave away its H. So that's called an enolate. And when you have this enolate, to stabilize it, you just do another proton transfer. Always when you're doing this keto-enol tautomerization, you just do two proton transfers. After this first step, the OH minus turned into water. And so water can act as an acid here. And this oxygen can steal one of the hydrogens, the electrons can snap back onto the oxygen. Notice this again is a proton transfer. It's our second one. And so what we end up with is the enol. En because double bond, all because OH. Notice the difference between an enol and an enolate. The enol has the hydrogen, the enolate has a negative charge instead. So you can see that you can get this keto-enol tautomerism. You can go from a ketone or an aldehyde to an enol with a base, in addition to with an acid. And so throughout all the reactions in this chapter, we're going to see that the first step will always either be adding an acid or adding a base. And that's going to make that alpha carbon nucleophilic. So it opens it up to reacting as a nucleophile. Now, there are two enols you can get here because you have two alpha carbons. So I'm going to quickly go through what can happen to the other alpha carbon, the other enol you can form here. So we talked about the one on the right already. You can do the same two steps on the other side. Do a proton transfer, the base steals the alpha hydrogen, the electrons snap back onto the alpha carbon. That's a proton transfer, and it leaves you with a resonance stabilized negative charge on your alpha carbon. That lone pair is allylic to the pi bond, so it exists in resonance. So you draw brackets and the special resonance arrow, and when you have an allylic lone pair, the other resonance structure, to draw it, you move the lone pair to create a new pi bond, and you break the pi bond to create a new lone pair. So the other resonance structure here would be this one, and so we have our enolate. When the base stole the hydrogen, it became water, and now it can act as an acid. This oxygen steals the hydrogen, the electrons snap back onto the oxygen. Notice that's another proton transfer, and at the end you have your other possible enol. So from that original molecule, you could get two possible enols. One if there's an alpha hydrogen on the right, and one if there's an alpha hydrogen on the left. The big point in this, though, is that the alpha carbon, whether you have acid or base as your first step, acid is in the previous examples, base is in this example, either way, you turn that alpha carbon into a nucleophile. And so that we're going to use that concept. We took a bunch of time explaining it in this video. I'm going to just assume that you understand that concept in these future videos so that we can talk about larger processes and bigger concepts that build off of that.